Well, in this video, we'll just do a couple of examples that are related to geometric series. In the first one, we got a picture of a bunch of circles, and the areas of the circles are listed, at least for the first four that were big enough here, but the pattern continues. We need to find the sum of all of these areas, all infinitely many of them, added up together. All right, well, the first question is, how do adjacent pairs of circles compare in area? Here's the areas. That's area 1, area 2/3, area 4/9, and so on. In other words, what do I multiply 1 by to get 2/3? Well, 1 times 2/3 gives me 2/3. What do I multiply 2/3 by to get 4/9? Well, that would be 2/3. 2/3 times 2/3 is 4/9. And then what's 4/9 times 2/3? That's 8/27. So we do have a common ratio. That common ratio is 2/3. That's what we call little r. So now r is, notice, less than the absolute value of r is less than 1. It's 2/3. Therefore, this sum is going to converge to the number that we will use the formula we learned in the previous video. So the sum, let's first do a little bit of work. Let's write this out to make it obvious it's a geometric series. 1 is 2/3 to the 0 power. 2/3 is 2/3 to the 1 power. 4/9 is 2/3 squared, and this is 2/3 to the 3rd. The next one will be 2/3 to the 4th, and so on. So if I take 2/3 to the 0, remember that's just 1, 2/3 to the 1 plus 2/3 squared plus 2/3 to the 3rd plus ... I have my infinite geometric series, and the ratio absolute value is less than 1. So this is going to equal, I'll write down the formula. Remember a over 1 minus r, where a is the first term. And what is our first term? It's just a 1. 1 over 1 minus the ratio, which is 2/3. So let's figure out what that fraction is. That's equal to 1 over 1 minus 2/3 is 1/3. And 1 divided by 1/3 is the same as 1 times the reciprocal of 1/3. That is 3. So the sum of all of the circles is simply the number 3. Nice geometric series. Okay, fractals. Well, fractals, they're typically described as self-similar patterns, where it means they typically look the same from near or far. Like, these are all circles, right? If you went to one of these really tiny circles and zoomed in on it, well, it would end up looking kind of like the original circle. They're all kind of the same shape. Or they all really are the same shape, just different sizes. All right, our last example in this video is going to be called the path fractal. More specifically, it's going to be called the hat fractal. Hat fractal. So we've got 4 stages, 0, 1, 2, and 3. We need to finish up stage 2. Notice stage 2 currently looks kind of like stage 1. Well, we're going to have to modify it so that it's stage 2. And then what we will do down here, it says, assume the length of the path in stage 0 is unity. In other words, 1. So we'll assume the length of this line segment is exactly 1. Determine the lengths of the paths here, here, and here. And then what is the limiting path? All that means is if we went to stage 10 and 100 and 1,000 and 1,000,000, what number would we be approaching? Okay, well, here's where we have to do most of the hard work, and it's not even very hard. What did I do to get from this line segment to this hat? Well, basically, you took the line segment, and it looks like we removed the middle 1/3 of it, right? And then we went up, to the right, and down. So I know for sure that this length is 1/3, just this little segment here. And then how much did we go up? We went up that same amount, 1/3. And this is 1/3, because we removed this section, which was 1/3. That's 1/3, and that's 1/3. All right, so what is our length here? In stage 1, what is the length? Well, how many thirds do we have? 1, 2, 3, 4, 5 thirds. Or 1 2/3. So we went from length 1 to length 1 2/3. Well, what are we going to do with stage 2? We're going to do similarly. In other words, this line segment, every one of these 1, 2, 3, 4, 5 line segments is going to become a hat, kind of like this one. So for stage 2, I'm going to remove the middle 1/3, and I'm going to go up, right, and down and make a hat out of this segment. Then I'm going to make a hat out of this segment, this one, and this one. So I've got it dotted here, basically what stage 1 looks like. I kind of went through and put a dot in on the 1/3 sections. So the first line segment, this guy right here, is going to have a pop-up in the middle. Just like that. So we're turning every line segment into a hat like this. So what are we going to do with this line segment? Remove the middle, and we go like this. So you can see that this line segment became a hat. And then this line segment, the top horizontal line segment, is going to look like this. And then like this. And then the last line segment, this one right here, is going to turn into a hat. So we need to go, and notice they kind of meet right there. And that's what we get. All right, so what is the length of the line segments? If you were to take the path all the way around like this, add up all these little tiny line segments, what do we get? Well, now each one of these little line segments is 1/9. 1/9, 1/9, 1/9, 1/9, 1/9. 1/9, 1/9, 1/9, 1/9, 1/9. Well, should I figure out how many that is? Sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 24, 25. So this is length 25 over 9, because each one of them is 1/9. I'll even make a note, 1/9, and I'll put an arrow there, and I'll put an arrow there, and they're all 1/9. Well, what's another way of writing 25 over 9? How about 5 over 3 squared? So we're starting to see the pattern. This length was 1. This length was 1 times 5 thirds. And this length is 5 thirds times 5 thirds. I'm going to expect this one to be 5 thirds times 5 thirds to the third power. And it turns out, of course, it's going to be. So what we're doing in this case is we're taking each one of these 1/9 length line segments and we're converting it into a little tiny hat. So let's take a look at this one in particular right here, just that one little line segment. It became that hat that I just circled here. Oops, I should have gone down to there. Right here. Okay, so each one of those little segments became a hat, which means we're multiplying it by the same ratio, 5/3. So this length equals 5/3 to the third power. It's the previous length of stage 2 multiplied by 5/3. So we indeed do have a geometric series. So this, actually, what stage is this? It's stage 3. So we have stage 0, 1, 2, and 3. Assuming the length of the path in stage 0 is 1, we already assumed that. Determine the lengths of the paths in this should say step 1 through 3. So let me fix that. 1 through 3. And then what is the length of the limiting path means as n goes to infinity? Well, if we notice, we go from 1 to 5/3 to 5/3 squared to 5/3 to the third. They're all positive numbers, and they're increasing positive numbers. Is this going to converge to a finite number? Absolutely not. It's going to keep getting bigger and bigger and bigger infinitely. So in this case, r equals 5/3 in our geometric series, but that's greater than 1. So it doesn't converge. The limiting path is going to go to infinity. So I'll just make a note. Limiting path goes to infinity, which is very interesting. You've seen stuff like this in calculus. If you took calculus, the entire fractal path at each stage can be drawn inside this circle or whatever oval shape this is. Yet, as n gets bigger and bigger and bigger, it's going to approach a path of infinite length. So it's a geometric series if we were to add it up, or actually each individual area at each stage as n goes to infinity, the length of the lines goes to infinity.